Okay, welcome back. So we were discussing the convergence of bisection method, and we have seen that it generates three sequences. One sequence is a sequence of an, another sequence is sequence of bn's, and the third sequence is xn. And what we notice that xn is related with the an and bn, such that xn is equals to an minus 1 plus bn minus 1 by 2. So this is how they are related, and we have seen that the limit of an is equals to limit of an and limit of bn are equal, and limit of xn is also equals to limit of an and limit bn, and the limit is nothing but the exact root of the equation f of x equals to 0, f of c is equals to 0. So it says that then the bisection method, so this sequence of approximation, the sequence of it generates a sequence of approximations xn which converts to a root c with the following property: mod of xn minus c less than equals to b minus a by 2 to the power n. So if you look at it more carefully, that you have if I get the information from the previous part of lecture, that bn minus n is related with means bn minus an is nothing but the length of the interval an to bn is 1 by 2 to the power n time b naught minus a naught. So these relations are very much true. Xn is equals to an minus 1 plus bn minus 1 by 2. This is second thing what we have noticed. Okay. Now in the next, so xn is belonging to an minus 1 to bn minus 1. C is the exact root where the sequence converges. It lies in all the sequence of these sub intervals ai comma bi's. Okay, in the next case an is equals to xn and bn equals either an equals to xn or bn equals to xn, depends on the sign of f of xn, or if it becomes the root, then you are stopping there. Now it is very much clear that c is means you are taking large enough n, means large n, such then you can show that mod of the mod of xn minus c, the difference of approximation root and exact root, is not going to be more than the half of the length of the interval an minus 1 to bn minus 1. That is very easy to clear. Very easy. So if this is an interval an minus 1 to bn minus 1, if this is here, so where is xn? Xn is this. So either c lies this side or that side. So mod of xn, so if it is less this side or this side, so it always be smaller than the half of the length of the mod xn minus c is less than absolute value of xn minus c is less than equals to 1 by 2 time bn minus 1 minus an minus 1, and which you again you use the result that they are related. So you use this successive or recursive relation here. So okay, so then you this bn minus 1 minus an minus 1 is 1 by 2 to the power n minus 1 time b naught minus a naught, and you club with 1 by 2, so this will be give you the result what we are claiming. Fine. So with this result is true now. Okay, so with the help of this result, what we can decide, we can work with the following problem: how many steps of the bisection algorithm are needed to compute a root of f with if the error tolerance is 10 to the power minus 6, given is a equals to 16 and b equals to 16. So the error, if you see, error is nothing but a difference of approximation root and exact root. So this is this mod of en. what you want, this mod en is less than equals to 10 to the power minus 6. So if this is if I mount this by 10 to the power minus 6, I am still be able to answer this question. So b is given, a is given, so 1 by 2 to the power n is less than equals to 10 to the power minus 6. So this will be 1 by 2 to the power n is less than equals to 10 to the power minus 6. Okay, 10 to the power minus 6. So this will be giving you 2 to the power n is greater than equals to 10 to the power 6. Now you can use just a calculator, or you can show that 2 to the power some 12 or something will give you result n equals to 16 or n equals to that will depends, right? N equals to 8 is 2 into 2. Yeah, something like 2 to the power 16, 17 or 8, something 9, or maybe 2 to the power 19 somewhere nearby. So n equals to, and maybe greater than equals to 18 or something will be there, will be the answer. So that you can find out by just performing different values of n. So that 2 to the power n is greater than, and you can collect the list value which satisfy this. This will give you the, that is minimum number of steps of the bisection algorithm are required to compute the root. Fine. So these are the following conclusion by looking at the previous problem. So we the method itself, you are nowhere using the values of the function at different points like ai's or bi's or xi's. Only you are working with the sign of fx. So therefore most of the time we are saying that this method is independent of f of x. You can actually decide the number of steps required if you know the starting and the starting interval, right? Other thing is, we all this generate a sequence xn such that it always converges to the exact root. So this method never fails. And the very other important thing is, you can show that mod of en plus 1, if you are able to recall this notation, is almost equals to 1 by 2 mod of en for large n. That also can be shown by just following as we have followed in the previous result, says that mod xn minus c is less than equals to 1 by 2 to the power n times b minus a. So that can be shown. So this says that this method converges linearly with asymptotic error constant 1 by 2. Okay, fine. So as discussed, these are things are there. Okay, so the next important method is very computationally effective method, or you can say which may reduce the cost of the which may reduce the cost of the solution for achieving the solution. That is Newton-Raphson method. So this method, why it is so favorite? It do have some advantages, very good advantages, but also it has some disadvantages that we will discuss hereafter. Okay, so again we are trying to solve f of x is equals to 0. We are solving this non-linear equation f of x equals to 0, and we have seen that bisection method is convergence is linear, so we require some faster method. So that, as in discussion in the first lecture, that the Taylor's theorem will give you the methods. It may give you it may design different type of methods which may achieve higher order accuracy, right? Okay, so assumption, the first assumption is let R be a simple 0. r be a simple 0 of f of x. That is means f of r is 0 but f dash of r is non-zero. That is very much required. You will see soon that why simple 0 is required. If what happen if multiple root, if it is a multiple root. Okay. Other thing is other condition is the function f must be differentiable. So like r be a simple 0, it must f dash of r is a non-zero. Okay, then the function and also you are assuming that f is differentiable in the neighborhood of r. That is also next essential thing, because we are going to apply Taylor's theorem, and Taylor's theorem, if you are recalling, that a series expansion that actually uses n number of n time differentiability of function f if you wish to open up to n plus 1 terms. Okay. The third important thing is a second derivative exists and is continuous in the neighborhood of r. So you require the differentiability of f, and the second derivative exists means f dash is also differentiable. So f comma f dash are differentiable in the neighborhood, and second derivative do exist and is continuous. You require the second derivative continuity, right? Okay. So then what you are doing is you are starting with, you are starting with an initial approximation x naught, and your new approximation is x1, that is achieved or obtained by just making the correction h to x naught. So x naught, why it is called correction or not addition or something, that will also be soon later. Okay, so that it becomes a good approximation for the root. Okay, right. So what happened here is, so let's have, so Taylor's theorem implies what? So Taylor's theorem implies that the new x1, so x1, what is the h is the correction, so that your new approximation is x1, and suppose that this is exact root r. So f of r is 0, that is equals to f of x1. F of x1 is x0 plus f of x0 plus h, and if you open it by using Taylor's theorem, that is about the point x0, it is first term is f of x0 plus h by 1 factorial f h by 1 factorial f dash of x0. Another last term is here is, if you see, h square by 2 factorial f second derivative at z, where z lies between x0 and x0 plus h, right? Okay, so this is and a higher term, or you can say this is a, if you are not stopping with here, so Taylor's theorem implies, so you are having OH square, big O, with either h square or h cube terms are involved here. So this Taylor's theorem implies this. So what in the Newton-Raphson method do is, it is neglecting this term here, and this it is assuming that this is an approximation, means like f of x0 plus f of r. Okay, this is using this is using this as a approximation, good approximation. x0 plus h is the approximation of r, means h is the correction. So what will it will give? So if you neglect this OH square here, so what you will get is 0 equals to f of x0 plus h time f dash at x0. So if you neglect the OH square term, you will get this. So from here you will get this correction term, h is equals to minus f of x0 divided by f dash of x0. So your new approximation r, or you can say x1, that is equals to x0 plus h, that is x0 minus f of x0 divided by f dash at x0, f dash at x0. So again, then suppose another correction you will make to x1, so that x1 plus h will becomes r. You will get again a new approximation. H will be f of minus f of x1 divided by f dash of x1 and so on. So it will actually give you a scheme which I wish to write here. So if I keep on doing this, xn plus 1 is equals to xn minus f of xn divided by f dash of xn, where n is greater than equals to 0. N is greater than equals to 0. So this is how this scheme or this method is derived. So you are getting the new approximation x naught, means your initial approximation is x naught, and you are getting new approximation x1 by just making the correction of this term. Then you will make it x1, you start with x1 now, next step. Then you will get the another correction by just replacing here n equals to 1, x2 by x1 minus f of x1 divided by f dash of x1 and so on. So what you noticed here is this f dash of x naught must not be 0. F dash of x naught must not be 0. If it is 0, it will blow up, right? So at each stage you need to verify that f dash of xn should not be very small or very close to 0. Okay. So when you write the program, you should able to or you should have to break the loop whenever you have mod of, means you have to define this condition, mod of f dash of xn is less than epsilon. Means epsilon you can decide some 10 to the power minus 4 or 10 to the power minus 3 and so on. That is very important here. Other thing is, suppose f dash of xn is non-zero for all n, then if f of x1 is 0, f of xn is 0, you will obtain a same, means xn plus 1 is almost equal to xn. So that you will control by taking the another criteria, that mod of xn plus 1 minus xn is less than epsilon, or you can go for in a relative sense. And another is mod of f of xn is less than epsilon, and the last one is the number of iteration you can fix. So this is what is happening in this Newton-Raphson method. Okay, so right, so this is how we will proceed to derive the Newton-Raphson method by using Taylor's theorem. Okay, so now let's try to understand what is happening geometrically. So for example, this is, let's say this is the here the given here curve is this by this red curve here. This is your y equals to f of x. Okay, this is y equals to f of x. What is happening is, here you choose an xn. Your new correction term is xn plus 1. How will you obtain is xn equals xn plus 1, xn plus h. It may be on the left or it may be on the right. So that's why it's plus h. We don't know whether h is positive or h is negative. So you can see here, this is f of xn. This point is you can say xn comma f of xn. Okay, so what you draw is, at this point, passing through this point, you draw the tangent where it will intersect. So this will intersect the x-axis. Certainly this will intersect the x-axis if the curve is like this. Okay, so the shape of the curve is very much important, you will see. Okay, so that is very important. So that is why you need to have some intuition, or you need to relook, or you have to try to figure out what will be the possible shape of the f. Okay, so once you know that, it's fine, so you can start working with. Okay, so xn, you draw the tangent. So tangent equation is given by this to the at the point f of xn, and that is actually a good approximation. And L of xn plus 1 at x equal to xn plus 1, this is intersecting x-axis. So this is your x-axis, this is your y-axis. So L of xn plus 1 equals to 0 will give you here xn plus 1. So this scheme will be given obtained directly here. So this scheme can be obtained directly by just substituting xn. So see how much faster it is jumping towards the root. Now what you will do, you will see here. Now you draw another tangent passing to this. So that will be xn plus 2 and so on. Then you will have this and so on, and it will converge faster to the root r. Okay. So when if you really want to know when the method may fail, okay, so it is very clear that the initial approximation will play a very important role. Okay, so let's take one example of case of failure of Newton-Raphson method. So if you have the following graph of this f of x, this is here f of x, this is here f of x curve. Okay, and let's choose this your x naught. Here is this here x naught. Now you have this corresponding f of x naught, and find and write the and get the tangent to this. So once you draw the tangent, it will intersect this x-axis at this here. So if once it x-axis, so you have to get the corresponding point on the graph of the curve, that is here. Now if you draw the curve to the tangent to this curve, this will be intersect here at x2. So next step is x2. Once you get the image of the x2 and you try to draw the tangent to this, it will be nothing but the parallel to x-axis, and you are gone, right? It will never intersect the x-axis. So it's a case of failure of Newton-Raphson method. Means tangent is 0. Right? So this is where the case of failure. So here the choice of x naught is also very important. So poor choice of x naught may result in a very weird situation as well. Right? Okay. So here is the step by step. Starting with point x naught, we pass to a new point x1 obtained from the preceding formula. So preceding formula is given by xn plus 1 equals to xn minus f of xn divided by f dash of xn. So it will produce a sequence of points x0, x1, x2 and so on. So here definitely n must be greater than equals to 0, and n is a natural number. What other thing you make to sure is f dash of xn is non-zero. You have to make sure this condition at each step. So let's find out let's solve this following problem. So find the real roots of the following equation: x cube minus 5x plus 1 equals to 0. So initial approximation is given to you, x naught equals to 0.5. Okay, right. So we have to solve this equation. So you have given x naught equals to 0.5, f of x is x cube minus 5x plus 1, f dash of x you can obtain, it's a polynomial, you can differentiate, so 3x square minus 5. So for first approximation x1, you have, if you use the formula x naught minus f of x naught divide by f dash of x naught. So you can use the calculator. So this is equals to, 0.5 minus f of 0.5. So if you try to find f of 0.5, that will be minus 1.375 divided by f dash of x naught, that is minus 4.25. If you solve it, so simplify it, this minus will get cancelled. You will simplify it, it will be 0.17647, which we will keep with 4 decimal places, 0.1765. Now similarly, x2 equals to x1 minus f of x1 divided by f dash of x1. Of course, at each step you have to make sure f dash of x naught, f dash of x1 are non-zero. So if you x1 is 0.1765 and f of x1 and f dash of x1, if you calculate by using Calc and substitute, what you will get is 0.2016. And similarly, if you try to obtain x3, that will also, if you up to 4 decimal places, that will be 0.016. So you can stop when you're doing manually and you are matching up to 4 decimal places. Yeah. Okay. So the question is whether always the generated sequence xn plus 1. So at each step you are getting new xn, right? X naught will give you x1, x1 will give you x2. So you are generating sequence of numbers. Whether it always converges to the root r. That's a very important question. So as you have seen 2 different examples, where in the one example you have seen that actually converges. In the other example, you see that fails, right? So it depends. So what is the guarantee then? That is given by the following result, that let f dash and f double dash be continuous. So means f is 2 times differentiable and the second derivative is continuous in a neighborhood of a root r. And f dash of r is non-zero. That will give you guarantee that r is a simple root, simple zero. So if the initial approximation x naught is sufficiently close to r, so how do you make sure that is sufficiently close to r or not? That's a very this question is very having a meaning, having not actual clear meaning, but it is saying that it's sufficient. You have to be very careful in choosing x naught. That's what it means. Okay, and try to choose x naught very close to r. That's what it means, I can say. Then error, then this happens. Means you have, if I will wish to write, this is equivalent to mod of en plus 1 is this, if I call as m time mod of en square. Means here the convergence is quadratic. So here quadratic convergence. If the method converges, it converges quadratically. Means double. Means you require to go for only few steps to achieve the root if it converges. Okay, so how to obtain this estimate is very simple. How will you proceed with that is so this is here is, you know, the scheme is given by xn plus 1 equals to xn minus f of xn divided by f dash of xn. So you difference by r both side, this by r. So this will implies en plus 1 is equals to en f dash of xn minus f of xn divided by f dash of xn. Right? So xn minus r becomes en, and you take the f dash of xn LCM in both. Now you look at this here, you look now, 0 equals to f of r, that is equals to, what is r is f of xn minus en. You know that f is continuously differentiable up to second derivative. So I can open it at about the point xn. You require about the point xn. So what is happening here is, so I can write this as f of xn minus en f dash of xn plus en square by 2 factorial f second derivative at gn, where gn lies between xn and r. Gn lies between xn and r. So if you see 0 equals to this, so this tells you that en time f dash of xn minus f of xn. From there you can get that this is equals to en square by 2 factorial f second derivative at f second derivative en square by 2 factorial time f second derivative gn divided by f dash of xn. And for sufficiently large n, gn and xn are close to r. So that's why here it's approximately equals to 1 by 2 factorial f second derivative gn is approximately f second derivative of r divided by f dash of r divided by f dash of r time en square. So this actually proves what we wish to establish. Okay, so this actually tells you that en plus 1 is approximately equals to 1 by 2 factorial time this for large n. This is true for large n. Okay, so this tells you that the Newton-Raphson method converges quadratically. Okay, or order of convergence of Newton-Raphson method is 2. This is a very important question. Sometimes it is also asked directly in your GATE exam as well. You will see. Okay, fine. Okay, so with this, okay, fine. So what we can draw the conclusions now. So from this method we can draw the conclusions that it requires the differentiability of f in the neighborhood of r. Second, if r is a simple 0 and x naught is sufficiently close to r, then this method converges quadratically to r. That's the last result of our Newton-Raphson method. The next is poor choice of x naught can generate successive points recede from r instead of converging to r. That we have seen from the example. Right. So therefore, what are the suggestion is, one must have some insight into the shape of the graph of the function. So for doing this, choosing x naught sufficiently close to r, what you can do is, you first apply some few steps of the bisection method, and then you get a good approximation, and then start applying the Newton-Raphson method to get the convergence, guaranteed convergence, or not. You cannot say guaranteed, but the thing is, it again depends on the good approximation of x naught. So you have to perform, if you perform the few steps of bisection, you are getting closer to the roots. So do some few steps, means like 10 or 5 or 6 steps at least to go towards the root. Then you start with the method, so then it will converge. Okay, so now this question is very interesting, that if R is a 0 of multiplicity m greater than 1, means if R is a double root or root 3 times, what can you tell about the convergence? Whether it still converges? Yes, it does. Okay, and then you have to show that if it does converge, it will converge linearly. So you have to go for the similar scheme, that xn plus 1 is equals to xn minus f of xn divided by f dash of xn, and try to show that this method converges linearly. So let's say, so if R is a 0 of multiplicity m, means more than 1. Okay, so that you can do as an exercise. It's a very simple exercise to do that. Okay, so what you will do to achieve the quadratic convergence is, so you have to modify this method. So for modifying this method, you can do multiply here by m. Then you can show that this mutant, again with the same way, you just subtract r both side and try to express by using Taylor series. You will achieve the quadratic convergence of this modified Newton's method. Okay, so that this quadratic to a root r. So you hint again. So here is hint is also given to you. Use Taylor's theorem, Taylor series for each of f of r plus en and f dash of r plus en. Okay, fine. So this again, one more application of Newton-Raphson method is in solving implicit functions. So first assumption is, so implicit functions means like you have the equation like g of x comma y equals to 0. So you cannot you cannot express y as a function of x only. Means this is an implicit equation. Okay, implicit function. So what you will do in that case, still Newton-Raphson method will play a role to get y if you prescribe x. So you need to prescribe x. Okay, if x is prescribed, then the equation can be solved for y. So x is prescribed means for x equals to, let's say, 0 or 0.1, this is fixed, and this is a function of single variable function of y, and you will have, so then Newton's method says that you have to start with y naught, and what will be yk plus 1 is yk minus g of x comma yk divided by g derivative. So here you have to have partial derivative, dou g by dou y x comma yk. So this will be the scheme, and k equals to starting from 0, 1, 2, 3, 4 and so on. So can be solved for y using Newton's method. So you need to initially choose y naught and start working with, and you can, for different value of x, you have to start with different y naught. Okay, right. Or you can fix y naught for each case, and you can generate new y case. You are sure, right? So choose or given a suitable starting point. Either you choose or it is given in the problem. Find y1, y2 and so on by the following formula. So here g suffix with y stands for the partial derivative of g with respect to y. So here is one example for this. Produce a table of x versus y, where y is defined implicitly as a function of x. So the g is given here, and start at x equals to 0, proceeding in steps of 0.1 to x equals to 10. So you have to, each step h is equals to, at each step you have to move 0.1. So means there are 100 steps, you have to perform 100 number of times. Okay, so x is running from 1 to 100. Okay, and you are so y, so like suppose what is g of 0 comma y? So if x is prescribed, what is g of 0 comma y? That is 2y to the power 5 plus y cube minus 3. Okay, so in general what I can write is, so here instead of this I can so see, do what is here is, let's do this here. G of x comma y is given, so I require gy x comma y is partial derivative with respect to y is 10 y to the power 4 plus 3y square, that is gy. Okay, so yk plus 1 is equals to, so for yk plus 1 equals to yk minus g divided by gy. So they are at x comma yk. K is running from 0, 1, 2, 3, 4 and so on. So for x equals to 0, so if you suppose I take the case x equals to 0. So x equals to 0, this term gone, this term is gone. So, and you know, you can choose y0 is also 0, or I say I must choose 1. If I choose 1, then g of 0 comma 1 is 0, 0, 0, right? Because 2 plus 1 is 3, 3 minus 3 is 0. So I can choose y naught equals to 1. So this will implies g of 0 comma 1 is 0. What about gy 0 comma 1 is 13. So this will imply y1 equals to y naught, that is 1, minus g, that is 0, divide by something, that is 13, that is equals to 1. Right? Similarly y2. So what will be y2? Is equals to y1 minus g of 0 comma y1 divided by g of 0 comma y1 divided by gy of 0 comma y1. So gy so 0 comma 1, so at any stage, so if you say y2 is at 0.1, so what you will happen is, so you can generate this, and you can actually, that sequence will converge to the root. Okay, so this is we are actually trying to find y for a given x. Okay, so you just whatever the, so now at each step you will get y1, y2, y3, all are 1, 0, 0 comma 1, again 0 and so on. So at each step, so y1, y2, it will generate 1, and so at x equals to 0.1, y is 1. That's very clear. Now for x equals to 0.2, so for this here you can just run the loop for k equals to 1, 2, 3, 4, up to 4 or 5, it is fine. Okay, you can run for k equals to 0, 1, 2, 3, 4 when you writing the code for this. Okay, so some of the reasons, so if you, now the next step is x equals to 0.1 at x equals to 0. So earlier we have started with x equals to 0, now you start with at x equals to 0.1. So you fix 0.1, and then find gy 0.1 comma y, g of 0.1 comma y, and substitute here and find the results. So what you will obtain here is I have got in the following table as follows. So for 0 means point at x equals to 0, y will come out as 1 and z value is 0. At x equals to 0.1, it will be a little differ, 1.4 times 0 7, that still z value is almost equals to 0, and so on. So it requires 100 number of iterations total. Okay, right. So in this way you can proceed with the following method, and you can draw the following table by using the MATLAB code. This writing is a very simple. This very simple code you can in this. Okay, right. So next is also another application of Newton-Raphson method is solving system of linear equations. So let's take system of equation which involve only two variables, x1 and x2, and you are expected to find the possible solution, means like x1 comma x2 for this. So you have to, so again you will proceed in the similar manner as you have done for single variable case, means again you will take corrections in both the direction, x1 plus h1 comma in the direction of x2 plus h2. Then again you will take the help of Taylor series of function of two variables, and then you linearize it and neglect the higher order term. You will obtain the Newton-Raphson method for solving system of nonlinear equations. So that derivation is easy as earlier one. Okay, so what is that? Let x1 comma x2 be an approximate solution of above system. Let h1 and h2 be corrections, so that that x1 plus h1 comma x2 plus h2 will be the better approximate solutions. So then you have to use this better approximation, means at this point, at this better approximation, at this point f value, f1 and f2 values are almost equals to 0, and use the Taylor series expansion for this, and then linearization. So here this not that this partial derivatives have to be evaluated at the point x1 comma x2. You are opening the Taylor series about the point x1 comma x2. So this so then you just equate these, so you have these two equations now equals to 0. So you can find, and so you can write in matrix form. Okay, so that is like AH is equals to F minus F, and you can solve. So you can write actually in the matrix form that, okay, this is here. Okay, so if you wish to write it in max, this is f1 or this is here. So I may have in the next slide the matrix form. What you will get is the following. If I denote this as this is the coefficient of h1 comma h2. So if I write this as here h1 h2 is equals to minus f1 f2 at x1 x2. So Jacobian time. So if I forget this here, so this is the matrix, coefficient matrix of h1 and h2, this vector, and that is equals to minus f1 f2 vector. So that if you rewrite in the matrix representation, you will get this. So what you require is to find the unique solution. This matrix must be non-singular. Okay, so you will get this h1 h2 as minus j inverse of f1 f2. So, okay, so from this what you will obtain is this correction h1 h2 is equals to minus J inverse of f1 f2. Okay, and so now this is h1 h2, this is where here. So what is here is now x1 plus h1, x2 plus h2. So you can write this as x1 x2 plus h1 h2. So you can replace h1 h2 by minus j inverse f1 f2, and you will have the new approximation is given by the sum of these two. So this is how now you can iterate. Okay, so now similarly you can go for the new then x1 1, x1 2, x1 3 and so on. So here you will find the following method. Okay, right. So this is where we end here now. Okay, and we will see some of the examples in the next session.